It is my extraordinary pleasure in all of the LinkedIn adjectives that are available for describing an experience such as this that may never yet have graced the planet. I am now able to introduce to you Daniel Wrigley, a coworker of mine whose work I have shamelessly used and taken credit for numerous times. And he's going to tell you about some of that.
Thank you. Now that I already have your applause, I don't know what to aim for this talk. But let's see if I can entertain you for the next 45 minutes or so and share a story how we, together with the AWS OpenSearch team last year, tried to identify ways how we can optimize hybrid search. So, wrong button. So, about me, I mean, my colleague David already shared all the great stories about me. Now I can shamelessly plug Raj's photographer skills, which he showed off yesterday night at Cardinal Hall, and I guess at least one person had fun there. So that's me having fun at after hours at search conferences. If I'm not a speaker, I'm at least from 9 to 5 a search consultant, sometimes a little earlier, sometimes a little later, with open source connections, the sponsors of this and organizers of this conference. I'm also a volunteer firefighter. I'm a competitive air pistol shooter, so I don't only aim for precision at 10 in my professional life, but also in the shooting range. And I happen to be an O'Reilly author. I wrote the first German book on Apache Solar. I don't think that's the right crowd to promote this book. And I think it's also too old to buy, so please do not buy my book. I want to share a story about optimizing hybrid search, and to get us all on the same page, I will start with boring lexical search that we've already heard a couple of stories during this conference, but well, it's kind of hard to know what all the other speakers will share, so who knows what you need in your slides, so I just kept all of mine and I will now walk you through them. So lexical search, to get us all on the same page, is great if you want precise keyword-based matching. It's fast, it's efficient for the very efficient inverted index structure that kind of maps words to documents and provides you with very fast lookups. It works very well for structured queries, for high precision queries, basically. But, and we've heard that in the talk before, it needs careful configuration of text analysis and, well, neighboring elements like tokenizers, stemmers, synonyms to handle not the basic, well, string matching process, but rather advanced matching. It also struggles with long-tail queries or ambiguous queries. So searching for bank gives you all the documents containing bank, whether that's a bank to sit on or a bank to withdraw money from. So if you have two documents, you search for fruit, one contains fruit, it's a match, the other one doesn't contain fruit, but apple, that's kind of a sad story then. You don't retrieve that as a result. Now, hybrid search consists typically of more than just one search technique. So the second one here is vector search. And vector search aims to capture semantic meaning. So it tries to handle synonyms, related concepts, like out of the box. And it's more effective for long and natural language queries. So all the time when you have more maybe conversational kinds of search applications, you will typically rather lean towards vector search than keyword search based matching. But on the other hand, it's more expensive than lexical search. So you have to create embeddings, you have to run all your documents through encoders, and you have to store these embeddings. So it's computationally more expensive. Computationally more expensive means, well, more expensive in your money box. But on the other hand, you get something out of it. Another drawback is you will always get the k nearest neighbors, so the k most similar documents out of your index. And vector search doesn't really care how similar these documents are. So if you are a shop selling, I don't know, auto parts, and someone searches for jelly beans, they will be seeing the auto parts that are the most similar to jelly beans, no matter how far away that is. So that is definitely a drawback to take care of. So we are now talking about hybrid search. So we want to combine lexical search and vector search to get the best of both worlds. So we want to combine these two search techniques to actually improve relevance, to improve search result quality. So we want to have the precision and the term-based matching from lexical search, and we want to have the enhanced recall by capturing the semantic meaning via vector search. So examples, I guess everyone can actually guess here, so I'm not going through these. What we want to do is with hybrid search, we want to balance both strengths by, well, more or less ruling out the respective drawbacks. So if you want to think about that as an illustration, we have a user query that is more or less split into two queries. In our case, it's one lexical query, it's one vector query. Of course, you can construct hybrid search systems that run not only two, but maybe multiple, and not only a lexical and a vector query, but maybe also a knowledge graph query and whatever other queries you can think of. But we'll be sticking to the, let's call it, simple and straightforward approach of combining lexical and vector. The lexical query is directed against the inverted index structure. The vector search query, of course, against the vector index. So these are two different data structures that you will need. And then you have to combine the results somehow, and then you get one result list. You can have, of course, search systems that contain an inverted index and a vector index. So most current search systems provide you with that capability, be that OpenSearch, Elasticsearch, Solr, and all the other also newer players, a Quadrant, a Pinecone, etc. They can all basically do that and handle the combination for you, but of course you can also combine these manually. So this is just an illustration of how it looks like. Now, how do we combine these results from the different subqueries? There are basically two different types of approaches. One is linear combination or maybe arithmetic combination. The other one is RRF, reciprocal rank fusion. For linear combination, we need to make sure that the two different scores that we are combining, the lexical BM25 score and the dense vector similarity score, that we normalize both before we actually combine them, as they are not on the same scale. So those of you who know lexical search and BM25 scores, they can basically be unbounded. So you can have lexical scores between 0 and 1, theoretically. You can have lexical scores of 1,000 or 10,000, depending on how you actually configure your BM25 search system. And when you think about dense vector similarity, they are typically between 0 and 1 or -1 and 1 in that range. And if you combine something that's very large and very small, that can kind of be unfair or unpredictable in these scenarios. So we need to normalize the scores. And then schematically, I have a W1, a weight 1, and a weight 2. So we can say we want more emphasis on lexical search, or we want more emphasis on vector search, so that we can really balance both. So we have tunable weight parameters here. That's the upside, and it's also the downside, because we have to tune these hyperparameters, and also we have to think about score normalization. The other approach, reciprocal rank fusion, it doesn't really take the scores into account, it rather takes the ranks into account. So we disregard the scores, we only think about the ranks. when we fuse these two result sets. They are both fused with this, well, mathematical formula that we have here. We have one ranking constant k that we can actually tune in this case, which gives us a certain amount of tunability, but a limited on the same scale, kind of. So we are less flexible, but it's also a more maybe straightforward approach. We don't need any normalization in that case. Our experimentation focus last year was the linear or arithmetic combination, so we'll be talking about that more. For one very simple reason, when we did that project, there was no RRF implemented in OpenSearch. Now it is. So maybe one of the next steps actually is rerunning that to identify if this approach is also applicable with RRF and not only the linear and arithmetic combination. So when we need to combine two things, we try to figure out how can we make, in this case, how can we improve search result quality, improve findability, how can we make, well, a tastier recipe. So we have ingredients, but we don't know how much of which ingredient actually gets us the best results. So what we aim for is we want to have one systematic approach to actually improve search result quality. Those of you who were at the meetup on Tuesday have to go through this circle again with me. Those who were at my workshop on Tuesday and at the meetup have to go a third time through this circle with me. I'm sorry, but I can't explain how important it actually is. So if you take something away from this conference, maybe it's this one here. So what we need is we need to gather relevance judgments. What's a judgment? We had that in other talks as well. So we need to infer document relevance for each query. We can do that by collecting user signals, like we've heard from Aruna in her UBI talk. We can ask human experts, or we can ask large language models, which we've also heard in several talks of today. So we need a way to say how relevant is a given document for a query. With that, we can calculate our favorite search result quality metrics. So we've heard a couple of these also during this conference: NDCG, DCG, MRR, recall, precision, mean average precision is one that we've heard of this morning. So there are a few. Choose your favorite or your favorite ones and go ahead. Once you have these search result quality metrics implemented, you can have a look at these and say, hey, what are my underperforming queries? And you can identify weaknesses, potential improvements, and say, hey, I can see that we have issues in, I don't know, multi-word queries, or in single-word queries that are very broad, in the very specific queries, long-tail queries. You can find out weaknesses and then start generating hypotheses how these can be improved. Sorry, wrong button again. Then you can formulate experiments. So you measure search quality for each of your hypotheses and then measure, hey, is this an improvement? Is this not an improvement? And then the most important part, you have to learn from each experiment and then evaluate and iterate on these learnings and insights that you had. If it's a positive learning, push it to production, at least in terms of an online test, an A/B test, and then the fun starts from the beginning. And this applies to all search quality improvements that you want to do, not only for those that are connected to hybrid search. So what were the hypotheses that we formulated for ourselves? When looking at arithmetic combination, we saw that we have this weight 1 and weight 2 parameters. So we thought of hybrid search optimization as a parameter optimization problem that we have. So hypothesis number 1, by identifying the best parameter set for hybrid search, we can outperform our baseline and have something that we called global hybrid search optimization. So what is the best global hybrid search parameter set that we can come up with? But we didn't want to stop there. We thought, well, if we have the best parameter set across all our queries, we don't assume that all queries actually benefit from it. So there will be winners, there will be losers. Some of the queries will be, let's say, will gain on our search quality metrics, some will lose. So how can we identify a way to predict per query individually and actually have the best parameters per query predicted by a machine learning model? So these were the two hypotheses we had, and we used the so-called ESCI dataset that you may or may not be familiar with. It was released by Amazon like 3 years ago for a competition. It has queries, it has product data, and it has judgments. So everything that we actually needed to have like, well, an experiment playground to do experiments with. We sampled 5,000 queries. We extracted all the different judgments. We created a lexical search baseline, not a very random one, so one that we thought, yeah, makes kind of sense. So we didn't like invest a ton on experimentation to find the best lexical search baseline, but we didn't just say, hey, we search across all fields and don't do any weighting. We kind of had a lexical search baseline, that put a strong emphasis on the title, on category matches, so something that felt good, made sense, looks good to me was the metric we applied here, basically. Then we set off and we just tried out all different parameter combinations. So how do we know which one's best? We know when we have tried all of them, calculated all the search metrics for all of these parameter combinations, and then, well, what is the maximum of this? So we tried the different normalization parameters, the different combination parameters, and the different weights for vector query, lexical query, which gave us 66 parameter combinations. And we just ran all of them. We calculated DCG, NDCG precision at 10. And then we knew, okay, this is the best global parameter set for hybrid search. Pretty straightforward. The Zorro team just mentioned they ran like, what was that, 72 experiments in the last 2 weeks. So that's 66 experiments that you can run in a day. And afterwards, you know what is the best hybrid search combination. So schematically, it looks like that. We identify the best hybrid search configuration that is like from a weight perspective here. The more left we go, the higher the lexical weight. The more right we go, the higher the vector query weight. And what we identified is that the ideal one is, I think the L2 norm parameter was the best one, and the arithmetic mean, and vector query weight of 0.4 and a lexical weight of 0.6. So this was the, well, global maximum that we reached, but we also knew that not all queries benefited equally. So if we have a query like black iPhone 14 Pro Max case, that is a very specific query. So if we apply the best hybrid search configuration, we may not have the best search result quality for this particular one. If we have a broad category query like smartphones and apply the same here, this may benefit. So from our judgment data, that may look pretty good. And then we have a third query here as an example, which is more an ID query. So a very specific one where there only is like one correct answer to this. Again, if we apply something that has a high lexical weight, that may be better in this case than having a 0.4 vector query weight, like in this example. So that gets us, well, somewhere, but maybe not ideal. So what we wanted is we wanted to identify a way that per query predicts the best hybrid search parameters for us. What we thought of is what are potential feature groups that we can come up with to actually predict these best parameters. We divided the features into 3 groups. We had query features, we had lexical search result features, we had neural search result features, and then we added as an additional feature the weight of the vector search query, so weight 1 in our hybrid search setup. I will show you how the training data looks like, and then we can dive into these different features in this overview. So we had per query 1 row. So we had 5,000 queries. We took 80% of these 5,000 queries, had a 80-20 test split, test and training split, sorry. So 80% is 4,000 queries, 4,000 lines of training data that went into our training data set. And you can see we have per query now what was the best NDCG value from our global hybrid search optimization process. With which vector search weight 1 did we reach this maximum? How many query terms does that query have? How many characters does that query have? Does it contain a number? Does it contain special characters? How many results does it produce when we run a lexical search? How well did it score best title score? What is the sum of all title scores, the maximum vector search score, and the average vector search score? So these were the, I think, 11 features that we had a look at. And what is interesting is we used NDCG as our target value, although what we really want to predict is actually the vector search weight. Why did we have to do that? First, we started out without the NDCG as a feature, and we only used the vector search weight. And actually we saw an improvement, but when we had a look at the R-squared scores per model, they indicated that the improvements we've seen, that they were purely random improvements that we saw. So we shifted our approach from predicting the vector search weight to predicting the NDCG score. And then we actually saw a shift in the R-squared score that gave us the confidence to know, okay, if we move from predicting weights to predicting NDCGs with the weights, that actually worked better. And we had confidence that this is then the better approach to go for, although it meant that per query we now have to run a couple of these predictions to know for which vector search weight do we actually have the maximum NDCG score, and then we need to kind of reverse engineer and know for which weight we had this to know what the best weight is per query. We did a lot of evaluation. We tried 2 models in general. So we tried out a linear regression model and a random forest regression model. So nothing really fancy. We wanted to keep it explainable. We wanted to keep it simple for the start so that we can really see, is there anything to this? Or is it just, well, did we just hope for the best but didn't really achieve anything? So we didn't want to go for like complex neural networks, but rather the simplest possible approach here. We ran cross-validation, 5-fold cross-validation. We had an 80-20 train test split, as I already said. We tried out all different feature combinations, so from different ones, only 1 feature, 2 features, 3, all the different combinations. We added regularization, so all the different, let's say, default machine learning best practices that we may or may not all have heard of. And then we had a couple of results. So the best root mean squared error that we had for linear regression was 0.23, the best one for random forest, 0.18. So you see random forest slightly more complex as a model and slightly better results. The feature combinations that we've seen, those that contained features from all the mentioned groups, that were actually the best feature combinations that we had. So it wasn't like, oh, just use query features, that's fine, or just neural search result features, that's fine. We had to go with all the different, or features from all the different ones to have the best results. But on the other hand, What you see here is the results of the 5-fold cross-validation runs that we did. These are the best, I think, 10 models that we had. And you see that these bars, they are very similar. So it's not like one feature combination clearly outperformed all the others. If you remove one feature and put another one in, they all like comparably scored equally. So the median is the bar that we are seeing here. And then as we have a 5-fold cross-validation, we have 5 root mean squared errors, and that's what these bars basically represent. So it didn't matter a lot for which of these best 10 combinations we went, but it did matter that we needed a feature from all of these different groups, actually. So what happens if we now go from what is the best global approach to what is the best per query parameter set? We now go in with a query black iPhone 14 Pro Max case, so that is the same as before. The dotted line is the global globally best parameter combination that we had, and now if we apply this, we may get a prediction that is slightly lower for the vector query weight. But it gets us better search result quality. So just an illustration of how this process now actually works. So before we were there, now we are way to the right. Now we pass in smartphones, we get, again, maybe this time a very high vector query weight in that case, because we maybe want a more diverse query set here, like we've heard in the Ask Me Anything session earlier today. Very general keyword, maybe we want a diverse query result set, so that kind of maybe makes sense from a thinking perspective. And search result quality again goes up from this mapping that we had before. Last one here, we search by ID. We don't really want to have any vector query weight in that case, and that gets us all the way up to ideal search result quality in this let's say, example that we are seeing. So that's how we went ahead. What results did we actually achieve? All metrics improved when we went from baseline, which are the light blue bars, to the global hybrid search optimizer, so the best parameter set globally, the dark blue bars, to the dynamic approach, which are the orange bars. So we already saw an improvement when we went from baseline to the global approach, and then we saw the next improvement when we went from the global to the dynamic approach. You see that the NDCG values and the precision values, they don't like knock you out of your seats when you look at the values that you're seeing here, so we don't really get an increase above 0.3. That's because we don't have 100% judgment coverage for all the data that we had a look at. So the ESCI data set is not a fully judged one. It has some gaps, so there still is maybe some uncertainty in this process. But altogether, as all the metrics for all different data set sizes that we had a look at, as they pointed in the same direction, the metrics were all good, the search quality metrics, the machine learning model metrics. That gave us enough confidence to actually, well, publish these results and also make this framework open source. So I will point you to the right resources at the end of this talk. So as we now know what are the results, a couple of production considerations if you want to take this and make this approach your approach. Offline testing is great. We've heard that from the talk before as well. So everything that we produced here was actually only offline tested, not online tested. If you have the best configuration, test that online. If you have the best dynamic approach, also test this online, of course. So only doing offline tests will not like prevent you from running thorough online tests, but offline testing gets you already very far in, like, well, get confidence in, is this really a good approach for your scenario? We tested out very general features, so not really any, let's call it, domain knowledge. If you try this at home, try to factor in as much domain and in-house knowledge as you can. So what I found interesting was, again, the Zorro talk. They had this query segmentation, so searches by ID, searches by categories, things like that. That can already tell you more about the query and maybe point you in a specific direction because it tells you something about, well, query specificity. So the query features we had may not be the best ones that work for you. Think about what might work best for you and then try and test and come up with additional ones that maybe get you even further. Identify low-hanging fruit opportunities first. So don't go from keyword search directly to hybrid search. There are a couple of, let's say, heuristics that you can probably come up with that get you already 1, 2, 3, 4, 5 steps ahead before you do something like hybrid search optimization. So we've seen the example like a query for an ID. That should never be a hybrid search query. So every time you can identify a query for an ID, go always for a keyword search query or maybe even for an, well, query by ID actually that most search systems provide. You might also have queries that shouldn't really be directed to your default index. So running an online shop and you have a query like return policy, that doesn't really look like a good query to search in your products for. So that may be something that you want to use a rule for. Your head queries may not be the good ones that actually benefit from this approach. So having maybe manually curated rules rather than a machine learning driven process can get you a lot further here than the actual hybrid search optimization process. Also, your baseline. If this is not optimized already, you can use this approach actually to maybe find optimizations for this baseline that you have instead of using this approach to, well, go in the hybrid search optimization direction. So I'm talking now a lot about do not use this approach, which sounds kind of weird, but what I'm trying to get at is you have to reach maybe a certain level of maturity where this makes sense, and there are a lot of other things to consider before going after a complex approach like this. Finally, a couple of shout outs. So this is not only my work, I'm, let's say, only presenting. Alexei Rodriguez, Vishal Patel were very strong on the data science side of things here. Jeff Samrick and Eric Pugh on the, let's say, wider product team, and Stavros here as a representative for the AWS OpenSearch team were also instrumental because they are kind of the sponsors of this project here. And with that, I say thank you. With the slides I will share afterwards, you will find the resources where you can find also the repository with all the information how we did that. So you can take it, try it at home. And if you have any, let's say, feedback, I would be very curious to hear how that works maybe for your applications, for your scenarios, because I don't think that this is the end of such an journey that we started here. I think this is maybe only a first step. So this can be taken a lot further. Query understanding to optimize search systems is, I think, a very wide field, and this only one aspect of it. So now I am very curious to hear your thoughts and questions. Thank you.
Thank you, Daniel. Are there questions?
Thank you. I might be imagining this, but I thought that there was some constraints on hybrid search as opposed to using either lexical or semantic search within open search. Is that true? And if so, how would that affect the ranking, like the ability to gather better rankings as opposed to being able to use more filters? Or if I'm just imagining this, that's fine too.
Can you repeat the first part maybe of the question again? Sorry.
Sure. I believe with OpenSearch hybrid ranking that there are limitations on the number of like filters and aggregations one can do.
So filters and aggregations in terms of really what you present your users as the like facet navigation, things like that.
Yeah.
Okay. Yeah. So that's a tough challenge, I think, because when you apply hybrid search, you only get a couple of lexical search results and a couple of vector search results, and that naturally like cuts off maybe at a point where you would still have additional ones that will provide your users with valuable filters and facets. So you may not really see all the different facet values that you may want to present your users with. So what you can do is run additional queries, so that you say, I run the lexical query next to the hybrid search query to at least have all these facet values. I think we are past the point where we always need to display the facet counts. So that is kind of a limitation that I think you can overcome by strictly not showing any facet counts any longer, because not all the search systems really supply that, and they are of limited use for the user. So what's the point of showing, are there 400 or 500 desks or 5 desks? Sure. So these are like my general thoughts. Get more queries that you get a sense of what are the popular facets, and then do something with that information with additional queries.
Good, thank you.
Can you speak a bit about the ESCI dataset and things you liked or didn't like? The judgments have like pretty low resolution. I think they don't take into account all the properties of the data, only the text part. Yeah, what were your thoughts?
So the ESCI dataset does not have any images, for example. That's right. So it only has a couple of product attributes. There is an extended version of the ESCI dataset that has a couple of additional features, and I think Roman, who is like the one who created this value-added maybe dataset, I think he wants to release a new version of that soon. Of course, there are limitations to that, because it's like ESCI, that's the classification system they use for the judgments. So E is an exact match for a query, C complement, S substitute, I irrelevant. So you have to map that to, we did a scale from 0 to 3, so 0 irrelevant, 3 perfect match. So that is something you have to do, which may or may not be good or bad. Yeah, that's just how we interpreted these. So these are like general considerations. Of course, judgment coverage is or can be an issue if you only have like 30% of your results covered with the judgments. That's not ideal, but at least it has judgment data, so it gets you at least to a certain point. So that's what we definitely liked about it. It is quite extensive, so a couple of gigabytes, a lot of queries, a lot of products. Don't nail me down on the details here, but do check it out. And if there are better data sets, I would be happy to replicate that for a different one.
Hi, thank you very much. When we tried to evaluate our hybrid search implementation against click model supplied judgments, we ran into the problem that, especially for long tail, especially where semantic search has a lot of impact, the data was very sparse when it comes to clicks, judgments, and then also presentation bias really kicked in. And I was surprised to see that you suggest using click model judgments to evaluate hybrid search in production. So maybe I missed something, or can you maybe say maybe there's some good tricks to employ?
Excellent question. Yeah, so judgment coverage definitely is an issue. So if you only have click data for lexical search and then you open the door recall-wise with a hybrid search environment, of course, unseen products will be flushed into the result set window, and unseen results mean for implicit judgments you don't have any implicit judgments for these. So good question. What you can try is you can see if you have maybe similar behavior for similar products. So something like maybe just a variant of a product was not seen, but the other variant was seen, and then you can like infer the judgment data from one product to another one. You can try something like map the query to a head query and infer some relevance judgments there. I think what maybe makes more sense is try and provoke implicit or user interactions for these unseen ones. So I think Doug wrote that chapter in AI-powered search, presentation bias and how to overcome that. So I think there are a couple of useful information nuggets how you can collect additional data that can then be used to calculate implicit judgments and then kind of get that wheel going. Of course, other strategies like LLM as a judge, they may fill the gaps as well, but that's kind of, yeah, initial thoughts that I have to that question and challenge. But yes, it definitely is a challenge.
Are there any other questions? Let's thank our speaker.
Thank you.